Hello, this is a review of the Tekbox 5 microhenry LISN. It's a model number TBOH01, and they also make a companion product that I really won't talk about a whole lot, but it's a device that helps you determine whether your noise or the signals you're measuring are common mode or differential. This is a pretty handy box. It is all metal and pretty good construction, and it's a very helpful device. What the LISN does is it allows you to measure noise coming in or out of a DC lines, and there are several standards that specify how much noise a device can inject back down the DC line, and one of these specs is CISPR 25, and in CISPR 25 they specify how the LISN should be built, and basically that's how it's laid out here. And the idea is that your device that you're testing over here will always see a typical or a standard impedance looking back this way, so you can get repeatable results when you move this your product that you're going to test from different power supply to different power supply. So I'm going to be testing a little DC to DC converter that I bought off of eBay, and this is made from a LM2596 National Semiconductor or TI part, Simple Switcher, and I have this configured so I'm going to be putting in 12 volts, and this pot will adjust it for a 5 volt output. The Tekbox LISN has a fairly complex circuit inside. It's different than what is called out in the CISPR 25, but it accomplishes the same thing in that it has 5 total microhenry. It has a little bit of extra filtering, and then it has quite a bit of protection for your spectrum analyzer. It has these back-to-back 5 volt ESD protection devices. It has a gas discharge tube that's will discharge at 60 volts, and it has these 5 volt ESD TVSs. So this is the your analysis side. So your DUT or EUT is on this side, and your source will be on this side. Interesting thing to note is how incredibly cheap you can buy these little modules. I just saw this one on eBay where they're selling 2 of these DC to DC converters with a buy it now price at 99 cents, and that's free shipping. So that's 50 cents a board, and the shipping is included. That's nuts. I don't believe how, I don't understand how they can make money doing that. So this is my setup. I have my Rigol DP832 power supply here, connected to the Tekbox LISN, then to the LM2596 DC to DC converter, and then right here I have a Rigol DL3021A electronic load, and I have it configured for 5 volts and a 3 watts. I then come down to out of the Tekbox LISN to a 10 dB attenuator, and then here's the spectrum analyzer, which is also a Rigol, my trusty DSA815. So here, listen. This is my attenuator. This is 10 dBs. Whenever I'm doing something with line conducted emissions, I'm always going to have my limiter in the circuit. This also has limiters built in. Can't hurt. This does not have a attenuation, however. An interesting feature to note about a LISN is that it can be used in either direction. So this side I'm going to have the Rigol lab supply hooked up to. My little DC to DC switcher hooks up to this side. But what's interesting is, since this has the impedance stabilization going on this side of the device, it also acts as a filter. And so if I had two unknown devices, I can swap this around and try and use the filtering characteristic of this 5 microhenries to try to determine from what side my noise is coming. I know that this is pretty darn quiet and this is going to be noisy. I'll flip it around and we can see the differences. Okay, we're all hooked up, and I have my spectrum analyzer currently set with a stop frequency of 30 megahertz. My amplitude has a reference level of 100 microvolts. You probably won't be able to see this in the video. My units are 10 dB per division, and I do have the compensation turned on for the transient limiter. You can see I've got about 40 dB background noise here, and I will turn this on. I also have a limit line set up here for 60 dB microvolts. So this is going to be my goal, is to get our noise below this. So we can see here that I do have quite a bit of stuff going on above the 60 dB line, and we're going to lower our frequency so we can see that a little better. Okay, so my stop is 5 megahertz, my start frequency is 9 kilohertz, and so we can see that there's a lot of stuff going on here. I'm going to even lower that frequency even farther. Okay, I'm set for 500 kilohertz. So we can see that we've got some interesting stuff going on here. And this is our first major peak, and that is 27 kilohertz. So that more than likely is the switching frequency of the National Semiconductor Simple Switcher. So remember this number, 27 kilohertz. It's going to be important a little later on down the road. So we've got this thing running. We can see the little LED on the DC to DC switcher. We can see that I have an output set at 5 volts. I'm currently running 3.5 watts, and we have got quite a bit of noise. I have a peak here that is 95 dB and 27 kilohertz. Let's remember that 27 kilohertz and 95 dB microvolts. I'm going to spin this around. We're lit up. We're still drawing the same amount of current. and we can see that this peak now is 77 dB. It was around 95 dB, so we're seeing about a 20 dB reduction in the noise. And so just the fact of spinning this around 180 degrees tells us our noise source. Since it's lower here, we can assume that the noise is coming from this, not from here. So I'm going to spin it around again. I just finished spinning it around 180 degrees. We're in our normal configuration, and I have a handful of little capacitors that I'm going to stick on the output, the input to the DC to DC converter, and we're going to see what type of reduction in noise we see over here. So the first thing I'm going to do is I just have a generic, this is a generic quality capacitor. It's a Panasonic, but just general purpose. And I have 89, let's call it 90 dB. So we saw a 5 dB microvolt reduction by using that capacitor. Here's a 1000 microfarad. Oh, value of this first one was 100 microfarad. This is a 1000 microfarad, or 95. $81. So a pretty substantial drop there. 95 to 81, so 14 dB. This is 100 microfarad. A lower ESR. $86. So that's a 9 dB drop, where this one was a 5 dB drop. This guy works quite a bit better in this scenario. Here's a normal little surface mount 100 microfarad. $89. So about a 5-6 dB drop. Okay, so let's look at some higher quality. This is a electrolytic, but it's a polymer electrolytic. See how much this has dropped? We're down to 82 from 95. So that was a 13 dB drop. So pretty crazy that this guy here is performing much better than this guy. Let's look at a ceramic. This is a 10 microfarad, 35 volt, in a 1210 package. You can see that, as expected, it really didn't do anything for this low frequency peaks, but it helps quite a bit for the higher frequency peaks. So this 60 dB is my goal. How can I get down below that goal? So I am going to try a more complex filter. I'm going to try something like this. I'm going to use two of these polymer electrolytics here and here with a series 1.5 millihenry inductor. It's ugly, but I just put it on, just tacked everything together and tacked it onto these banana plugs so I can easily plug it in and you can see the difference. So I'm going to save this file here. I'm going to trace. I'm going to blank everything. I'm going to max hold. Let's freeze it. Go to the next trace and insert the filter. Okay, it's plugged in, it's running, and let's get, look at that. That is amazing. So I have almost met my goal of hitting this 60 dB level here. Now you might be saying, if you've worked with these National Semi TI LM 2996 parts, that something doesn't quite seem right. This part is supposed to be operating at 150 kilohertz, and we can clearly see that we have a major peak at 27 kilohertz. And so this really surprised me for a minute. I looked at, so I took this guy and I put a scope probe and looked at the switching of the inductor, and sure enough, it really is switching at this 27 kilohertz and not 150 kilohertz. This part, the Simple Switcher, runs at a fixed frequency of 150 kilohertz, and it varies the duty cycle. And so this puzzled me for a bit, and I believe that this is a fake counterfeit Simple Switcher. I think that's the only explanation. It's fake. What else can I say about my setup? As I mentioned, this is designed to the CISPR 25 standard, and I think you could actually do this exact same setup and have a fairly high degree of confidence that you're going to meet the test standards at your compliance lab. Some things that I have done to get my results more accurate is I do have a ground plane underneath this cardboard desktop here. I'll pan down a little bit and it'll be hard to see, but right here is a piece of aluminum, and that aluminum foil, not aluminum foil, but that aluminum sheet, I have two sheets that go the depth of my desk and are roughly 3-4 feet long, and there's two of them, and those are all tied into earth ground. Well, that's about it for the test of this Tekbox LISN. Works really well. It's reasonably priced. They make several other products, like I mentioned earlier. They make this LISN Mate, which works well for trying to determine if your noise is differential or common mode. In this setup, everything is differential. They also make a very nice transient limiter. Looks kind of like this, and you always want to have one of those when you're looking at line conducted noise. They also make some other interesting EMI RFI compliance gear. I haven't tried it out just yet, but I did order it, and I need to give this a whirl. But this is a TEM cell made by Tekbox, and the construction is looks very good, and kind of excited to give it a try. This is a model number TBTC1. Anyways, kind of slick. That's about it for now. If you have any questions, let me know. Thanks. Bye.